Welcome from the U.S. Fish and Wildlife Service's National Conservation Training Center in Shepherdstown, West Virginia. My name is John Asana, and I'd like to welcome you to our webinar series held in partnership with the U.S. Geological Survey's National Climate Adaptation Science Centers. And today's webinar is titled Variable Warming in Lakes of the Upper Midwest and Implications for Sport Fish. And we're excited to have Jordan Reed from the USGS with us today. To introduce our presenter, we have Aparna Bamzai-Dodson. I hope I said that correctly, who is the Deputy Director of the North Central Climate Adaptation Science Center. Aparna?
Yeah, you said that perfectly. Thank you, John. So Jordan Reed is a USGS data scientist with a background in physical limnology and modeling. Jordan works with others to develop frameworks for reproducible research and data visualization and new methods that combine traditional process-based models with machine learning. Jordan approaches research questions that involve lake and stream simulations and sensor data analysis, including the challenges of modeling over tens of thousands of lakes across the U.S. As part of collaborating with regional and local scientists interested in climate impacts on lakes, Jordan is a principal investigator for the long-term ecological research North Temperate Lake Site, a lead PI on a project to model climate change impacts on lake temperatures, and has served as a steering committee member of the Global Lake Ecological Observatory Network. Jordan is an associate editor of the journal Limnology and Oceanography Letters and the chief of the data science branch within the USGS Water Mission. Thank you so much for being here today, Jordan.
Great, thank you. And I'm going to pop up my slides. Hope this goes off without a hitch, and I should be sharing. Can you all see my screen? If somebody can give me an affirmative.
We're good on this.
Great. Okay, well, thank you for the invitation and the introduction, Aparna. I'm really gracious for this opportunity to speak to this audience on this topic that I'm really passionate about, which is lake responses to climate change. I want to thank specifically my co-PI, Gretchen Hansen, who's at University of Minnesota, Twin Cities, and our many other collaborators, many of which I'll give a shout out to throughout this talk that have been working on this and related projects for years on this topic. And just reinforce that I'm speaking on behalf of a lot of partners, and we've had a lot of excellent support from the National Climate Adaptation Science Center and both the Northeast and the North Central Climate Adaptation Science Centers to get this work initiated and to move it along, in addition to our other funders, which I'll recognize at the tail end. So this talk will focus on lakes in the Midwest, and just to kind of set the stage here for this talk. When you look at an overview of the Midwest, lake features are something that really pops out. They're key elements in the landscape of the Midwest, and it's not just the Great Lakes. These lakes are numerous and they're prevalent. Likewise, these lakes are important for economy, recreation, cultural, and ecosystems. We really need to understand these lakes to make informed decisions that are related to either sustaining, adapting, or enhancing our relationships and expectations about lakes. Meanwhile, we're, of course, experiencing a lot of change in lakes, and I would argue that lakes are one of the areas where we see one of the strongest expressions of climate change. So several years ago, we published a study that assembled temperature data that was both collected in situ, meaning many of our partners went out and sampled these lakes over decades, and then we also put together remote sensing satellite records and put together this synthesis of trends showing that 90% of the lakes that were in this global study, which included the largest lakes on Earth, were warming, but also that this variability across lakes that there was a significant amount of variability in warming across lakes as well. Also, to go back to the Midwest, we're seeing a lot of change in fish populations in these lakes. So if we take a look at the regional or state level at fisheries data that can be aggregated together, we see a number of patterns that emerge, either increases or decreases. And just to point out a couple of them, we see in Wisconsin declines in really valuable cool water fish such as walleye. And then we see increases in some warm water fish. So in the lower left-hand corner, you see an increasing trend in largemouth bass across the state of Minnesota. But just like what I mentioned about warming trends in lakes, if you get down to the lake-specific level, you see a lot of variability in these trends. So in aggregate, the previous slide, we see trends up and down in key fish. If we look at individual lakes, we've got variability in these trends. So we need to understand specifics about these lakes that result in this variability in order to understand and manage expectations for the future. And these aren't just academic exercises where we want to hatch a question and maybe nobody's interested. This is critical information that the public is really keyed in on. So just a few highlights from some of Midwest publications that highlight changes and expectations for fisheries openings and declines. And we're just showing the headlines here. If you get down into the comment section, you'll see a lot of energy, a lot of excitement about either management decisions about these declines or about the experiences and the differences compared to one's childhood. So in order to address these particular problems, so understand changing climate and the impact on sport fish, we've established the suite of projects that are really centered around this Midwest Glacial Lakes Partnership, which is a fish and wildlife regional fish habitat partnership. It kind of forms the collaborative backing of this group. And I'm showing here just the spatial extent of that Midwest Glacial Lakes partnership. Within this project, we have two main goals that I'll talk about today. One of them is to leverage this cross-state data expertise and environmental gradients so that we can better understand climate change impacts on Midwest sport fish. And then the second one really seems to be a goal that goes hand in hand with doing any broad-scale work, which is the need to dig in and look specifically at often lake-by-lake management questions. So we want to augment regional predictions with local observations and knowledge to address critical lake management questions. And so for the remainder of the talk, I'm going to be focusing the first half on this project goal number one, and then the second half I'll dig back into lake-specific tools and questions. So for the first one, taking advantage of this spatial extent and the expertise that's shared across the academic groups, the federal partners, the state agencies, in sharing data and sharing knowledge in order to give us the appropriate models and data to answer these important questions. And I want to acknowledge this is a subset of the Midwest Glacial Lakes Partnership and the science and data team in-person meeting that was back in Minnesota. And I don't think this represents the entirety of that team, but getting together and providing some guidance and some backing for this project. And I just wanted to give them a shout out and recognize how critical they've been to establishing the direction of this particular project. So understanding warming and fish responses to climate change is often approached using empirical models that use often kind of air temperature as a proxy for water temperature, since we have air temperature observations in many locations. The air temperature change that we get off of climate projections is kind of often front and center for managing expectations for the future. And so many of us would build models that tell us something about temperature change or about water temperature change based on air temperature change. And you can see, here's northern Wisconsin air temperature versus water temperature. There's a pretty strong relationship there, and with some other predictors, you can expect to back out a good bit of that variability. But when we're looking at climate change, and specifically looking at conditions that in some cases are going to be warmer than we have yet to observe locally, we want to be a bit wary about the transferability of these relationships, both in space and into the future, so in time. So here, if we compare this to, and this is really just an example in Kansas to just highlight what happens when we get warmer and warmer, different lakes and different regions will kind of have a different degree of flattening out at the top here, revealing that there are some other important factors other than just air temperature warming rates that we'll need to take into account. So instead, our project has focused primarily on using a process-based understanding of the controls of lake temperatures, so that we can kind of get down to the root of what makes temperature change from a day-to-day and a week-to-week and a decade-to-decade sense, so that if we understand trends in those individual components, we can have better expectations for the future. So what do we need to do to build that process-based understanding of lake temperature change? Well, we need to know some things about the local climate of these individual lakes. Likewise, we need to know something about the size and the depth of the lake. So if a lake is very large and shallow, it's probably going to be fairly well mixed, meaning it won't have much of a temperature difference from the top to the bottom, versus a small, sheltered, protected lake might have a very warm surface water temperature, but then still plenty of good cool water habitat in the bottom. So those are important things for us to be able to include in our modeling approach. And then, like I mentioned a little bit before, the degree at which these lakes are sheltered from the wind. So understanding local canopy cover and its impact on kind of reducing these wind-driven fluxes, like the rate at which the lake evaporates and the mixing energy and whatnot. And then lastly, of these kind of high-level controls on lake temperature, the water clarity matters for the aesthetics of the lake and also for site-based predation, but it also, of course, has this impact on the vertical thermal structure of lakes. So a clear lake has deeper penetration of solar energy, so more sunlight kind of gets towards the bottom of a lake. Darker lakes are warmer closer to the surface because they have more of that energy kind of attenuated close to the surface. So what this means is all other things equal, that darker lake might be a bit colder in the bottom compared to the clearer lake. So we need to take all of these things into account. And by doing so, we can build these process-based, or some folks call them mechanistic models, that allow us to, on a fairly resolved time step, and in this case we're showing daily simulation, so a daily time step, to build a vertically resolved record of water temperature with the model. So with the caveat, if we have good information for all of those, we can do a good job with a model like this in reconstructing historical observations. So here is an example from northern Wisconsin, where just for one kind of summer season, we have a lake that has warmish temperatures, close to 30 degrees towards the surface, but then lots of cool water habitat towards the bottom, and you can see the model's ability to reproduce that in addition to its ability to resolve these warming and cooling fronts that move through. So if we were interested in this one lake, and if we had, say, fisheries observations on the monthly scale or sparser than that, we could potentially reconstruct this temperature record to complement that. So we would understand how temperature is changing and how that may explain some of the trends that we have in the fisheries data. But the real power of this type of approach is using these nationally available data sets and also a lot of manual digging to scrape PDF files for information on the morphometry of lakes and dig up old temperature records and all kinds of things to eventually put together the data needed to model lakes at scale so that we can build one of these daily water temperature models for all of the lakes of interest for management, including thousands or tens of thousands. So here I'm showing just a local snippet because it's kind of overwhelming to look at a animation like this at broader scale, but a local snapshot of surface water temperatures coming out of these simulations. So, you know, I think you've seen this through about once by now, and what probably sticks out to you is the relationship across these lakes where there's a lot of coherence. There's a lot of similar behavior as they march through the spring and into the summer. And then one thing to point out as you watch this a second time is you start to see a bit of this heterogeneity. So even though there's strong agreement in what's happening through these seasons, you see things like, oh, the smaller lakes kind of flicker a little bit more, the larger lakes are a little bit slower to warm in the springtime. And what we understand from evaluating these data and their relationship with the biological data that we also collect alongside is that these differences, although being somewhat visually small right now, really do matter. And we can take this modeled information and generate metrics that we consider to be relevant to our biota of interest, such as growing degree days. And so here we take that annual daily animation and we turn it into a single metric for a given year. So within a year, calculating the growing degree days for each individual lake. And there you start to see some of these differences across lakes that may not have been as visible on the daily scale. And we can map these out. And of course, here we're looking basically within one county. If we looked wider, we'd see a much wider spread of this particular metric as well. And what can we do with this metric? Well, Gretchen Hansen's work that was published back in 2017, and this used our models just for the state of Wisconsin, but evaluated this in addition to many other water temperature derived metrics to attempt to predict the probability of successful recruitment for walleye and the probability of largemouth bass relative abundance in these Wisconsin lakes. And with all of the temperature metrics that were fed into this model, most of those fell out as being either redundant or less important. This growing degree days popped out as being the key one. So if you are interested in this warming relationship where clearly these cooler lakes are all other things equal doing better for walleye recruitment success, but then as we move into higher degree days, largemouth bass relative abundance is expected to be greater and walleye recruitment kind of knocks off. These are really important. This is really important context to have for some of these patterns that we've seen in the state of Wisconsin and in other Midwest states. And likewise, we can combine those with the other elements of the model, including the depth of the lake and some clarity information and its size, and be able to categorize individual lakes as to whether or not they're more likely to be dominated by largemouth bass or walleye or potentially coexist. And Gretchen's work did this for the contemporary period with these available data and found that for the state of Wisconsin, that the majority of these study lakes were bass dominant. A smaller fraction, but which ended up being the larger of the lakes, was walleye dominant, and then a small fraction of lakes coexisting. And then what we're able to do with climate projections is to look at transitions through time. So as we move into a mid-century period where we've got warmer conditions, and of course a response from the lakes is also to warm up, we see an increase in the number of lakes that are bass dominant. Some of those are because we're potentially losing walleye lakes to become bass dominant, but in other cases we're creating new opportunities for bass by taking some of this neither category and moving those into the bass dominant. And then if we take that towards the end of the century, that pattern continues. And Gretchen's work in that study and in later work also looked at the lake-specific these lake-specific factors, such as the relationship that I showed with temperature is very clear and compelling, but there's of course caveats to that. That relationship is a little bit different when you slice it across lake size. So on the plot on the left, you've got lakes at about 100 hectares having this huge fall off in walleye recruitment success as in higher degree days versus lakes that are larger are maybe a bit more resilient to that warming. And then in the plot on the right, just a note that warming increases recruitment success in some lakes, but it decreases it in others. And the presence, in this case, of largemouth bass might influence that response too. So there's multiple lake-specific factors that may provide a different signal and need to be interpreted. So hanging on that point about lake-specific knowledge and its importance, gets us to the second part of the project goals. So, first we were using these broad gradients and this broadly available information and knowledge to generate models and some expectations. Now we're trying to do that very challenging thing where we take regional work and we make it locally accurate and locally relevant. I'm going to go over two use cases for how we've moved towards that in this project. The first of these is to make better predictions by taking more advantage of data in these models. And then the second of these examples is to include other factors, other dynamic factors that need to be taken into account locally. So for this one, we'll talk about thermal optical habitat for walleye in Minnesota. So the first of these kind of improve our local estimates, our local knowledge of change, is to improve water temperature models by taking advantage of local data. So I glossed over the modeling results that focus mostly on outcomes and on surface temperature metrics. And the hidden truth here is that despite putting a lot of energy and effort into this modeling approach, doing broad scale models still has its flaws. So at this scale, we have many cases where estimating deeper water temperatures or even water temperatures in the middle parts of the lake with respect to depth during the summer is challenging and fairly error prone. So here, this little plot, you'll see there's what is basically model residuals. So taking a model and then subtracting off what observations we have. we see that the model is off by, in some cases, as much as 5 degrees. And that's really not acceptable for use in these fisheries research questions, because it's just simply not good enough, which is why the work to date has focused on the surface temperature estimates, which are reliably better. But because we're really interested in getting those answers for deep water at scale, at this relevant scale for management to understand, we need to figure out if there are more possibilities available to us. So we started working with Vipin Kumar out of University of Minnesota Computer Science Department, who's really an amazing collaborator, and the work that he's done to date is very relevant, because he's looking at data-driven approaches for understanding climate impacts. And so we were able to start partnering with Vipin at an early stage in this to develop some new approaches for improving these models. And we've refined the language that we use to talk about these to kind of zoom in on this concept called process-guided deep learning predictions. And we've got a number of papers in various stages of publication, including one that is currently in review that I'm going to talk about for this use case. But it's been a really exciting research pairing with Vipin's group. And the question we have right off the bat is, we know that with some of these advanced machine learning modeling approaches, that we can beat these so-called process-based models. So the modeling approach I've been talking about here for the most part is process-based, meaning we constrain it with our physical knowledge of the system. But we can use a completely different approach, empirical approaches like regressions, or some of these more advanced machine learning approaches that really ignore these physical relationships and focus on the pattern in the data and how to reproduce that. And when there is enough information, those types of data-driven models really, hands down, can do a better job of reproducing the pattern than our process-based models. So that's kind of the right-hand side of this plot. With more temperature data, these models, a deep learning model is more accurate than a process-based model. But on the left side of this, if we have less and less data, in many cases with this type of work, we have no observations or they're very sparse, that's when this type of model, a process-based model, really excels. So our work with Vipin's group really went after hybridizing these two approaches. So went after including these process components into deep learning models. So what we're doing here is, if you think back to the early part of this talk where I was mentioning all of the different climate drivers that need to be taken into account to understand, the rate of evaporation in the lake and what incoming solar radiation and long wave radiation are, we were able to encode those modeling components into an otherwise data-driven model that learns from our existing process-based model. And the exciting part is, as I guess, of course, might be expected, it does better than both of the approaches in all of these conditions. And so what does this mean for our problem with model bias in the deep water? So it's really just one example here, but we can use these models to really do a much better job at these type of predictions, and thus we'd be able to, with more confidence, apply them to more thermal gilts of interest. And just to communicate where we are with this particular part of the project, so we've been working with Vipin's group for a year and a half now on developing and applying these methods and working on how to scale them up. Allison Appling, who's a USGS employee, has been working with their team as well to reconfigure their approach onto something that we can run on USGS infrastructure, and has gotten us to the point where we're able to run hundreds of models using this approach with available data, hundreds or thousands, to where our computing is no longer the limiting resource here. So moving on from process-guided deep learning improvements of water temperature and moving into very lake-specific applications of this type of work. So improving temperature is great, and those estimates are really critical for being able to say much of anything about broad-scale environmental change when it comes to lake fisheries. But in some cases, temperature alone is not going to give us what we need. So in Mille Lacs, which is a critical lake in Minnesota, we've got the most historically popular walleye fishery has been in decline while faced with several environmental and anthropogenic factors. So here's the time series of the decline, starting in the 90s and getting us close to present day. And we've got a number of ecosystem changes that are happening at the same time. So we have a clearing of the lake. So the water clarity is becoming clearer, and you may think, oh, great, better water clarity, that must mean the lake is healthier or better. You may not feel that way if you're a walleye, because you'd be a low light specialist, and you do better in lower light conditions as a predator. So you actually do better in these low transparency conditions. So if you're a walleye, you're fairly bothered potentially at this zebra mussel invasion. And at the same time, we have overlaid a period of warming. So when examining this problem, we need to understand the interactions between these water clarity changes and water temperature changes, and what that means for walleye. Luckily, we have some precedent here. In 2004, Lester et al. Wrote this paper on thermal optical habitat. So the idea of, if we can understand this intersection between the appropriate amount of optical habitat and the appropriate water temperature, that we can do a better job at predicting the success or sustainability of the walleye population. So if we are able to take incoming information about basically the solar radiation, so the visible light coming from the sun, how much of that is available at various depths, we can create a relationship for the ideal optical habitat for walleye. And we can look at how that varies through time, because we have an understanding of how the water clarity changes through time. We also can take our existing water temperature models and create those yearly metrics for thermal habitat using optimal conditions for walleye as well. And note here that we've got trends in optical habitat with a decrease. Thermal habitat is more or less the same, maybe a little bit of warming, and the thermal optical habitat itself has this decrease pattern. So how do we apply this? How do we take this information and turn it into something that would be useful for managers to understand and communicate? We can use the framework, the safe operating space, and apply it to this fishery in Mille Lacs. So say we've got a starting point where we've got a safe or sustainable space for this fishery, meaning if we keep operating in this area, we're not going to run into too much trouble with future populations. But environmental change can push us outside of this safe operating space, even if we're not modifying the harvest, so the amount of walleye that we're removing from the system. And usually once we get out into this unsafe spot, we might expect a management response to hop in and reduce the walleye harvest available to get us back down to that safe operating space. Alternatively, if we can understand and adapt to this change as it's happening, we can propose an alternative, more efficient pathway that keeps us operating within this safe space as we move through environmental change. And Gretchen, who's been very productive with this work at the intersection of climate change and fish, recently has a paper accepted in Ecosphere that applies the safe operating space with mille lacs and thermal optical habitat for the walleye fishery. So if you look at Figure 1, you note this. So this curve denotes there's a nonlinear relationship between habitat and safe harvest. When we compare it to a historical harvest, we can see that we've over-harvested about half of the time, give or take. In more recent years, we've been well within the safe limits. And just as a note, recreational harvest has been closed for much of the past 4 years due to low biomass. So yes, we'd expect that harvest in recent years would be within safe because it's been closed. If we shift over to how these data can help us understand these impacts for years out in Figure 2, in most cases, when harvest has exceeded what we've estimated as a safe harvest based on this thermal optical habitat, the population has declined the following year. So a pretty compelling example of how the combination of temperature change, optical habitat change, and also having appropriate information on the harvest pressures can really allow us to understand this change through time. And we can use this information not just in mille lacs, but at broader scales to really both manage our lakes and also manage expectations if we can make these connections with the data to the public. So I want to hop to just an overview of where we consider this project to be and what we're hoping to do next. I hope this has been a decent overview that gives you kind of the flavors of this project. It's been a really great collaboration that's included a bunch of dimensions that I hope I've done justice to within the time limits here. But I know there's of course plenty more to talk about and more questions that are likely to come up. But so what we're working on right now is finalizing and releasing these model runs at this expanded geographic scope. So this includes the Dakotas, includes some work in Iowa, and releasing those as one big data release package at this scale, at the Midwest Glacial Lakes Partnership scale for external and internal and all kinds of different uses. The next thing we really hope to do is to be able to go as far as we've shown in specific states. So the examples I've had have really been state specific. So Minnesota and Wisconsin, we really want to dig into more cross-site biological synthesis work. So the really hard part of meshing up fisheries data across states and using that to build multi-state fisheries models that really take advantage of these big environmental gradients so that we can get a better understanding and expectation for change. And then lastly, I didn't spend much time on this today, but we've been really focusing on making sure that any important scientific output that we've got that's in a traditional publication also is able to find its way into a public-friendly product that we can use for communication and expectation management. So we're pointing out a previous data visualization we did on the work that was specific to Wisconsin, and we hope to continue doing similar work to connect stakeholders with the appropriate tools and data that they need. And lastly, I wanted to thank the funders and partners that have made this work possible, and hope that there's a little bit of time for questions.
Okay, thank you. But I want to thank everyone who participated in the event, and I wanted to thank USGS and their help, and ELDA and all that with continuing this webinar series. Use the concept of growing degree days. Is that an air temperature-based metric, or is it adapted for aquatic application?
Good question. So if you're familiar with growing degree days, it's basically the cumulative sum of degrees above a certain threshold through a year or a season. It's common for ag, so usually that would be air temperature degree days, but here we're using water temperature growing degree days, so it is the lake temperature version of that, calculated in the same way that we'd calculate an air temperature-based growing degree day.
Okay, thank you, Jordan. What kind of fish are in the Neither Lakes? So the lakes that aren't dominated by walleye or the bass.
Gotcha. So I think question about the map we've got here. So the lakes that would be in black. I'm going to let Gretchen answer that.
Yeah, what fish are in the Neither Lakes? So that means that, so we classified bass lakes as where did they have a high abundance of largemouth bass? So it's pretty likely that those lakes still have some largemouth bass in them, because almost every lake in Wisconsin does. But they don't have natural walleye recruitment. They may also have walleye in them if the walleye are stocked. It's just not naturally recruiting. And then, there are a number of other species as well that might be there that we didn't model in this study.
Okay. Thank you. Leslie, does one of the publications out now further address your point, process-guided deep learning model performance superior for out-of-bounds data sparse, or out-of-bounds data sparse, data-rich conditions? Sorry.
So the only paper that tests all of those is the one that is in review right now, that I was showing results from. I'll just get back to, so these results are all from that paper, and I think this is the point that where this question is coming from, superior for out-of-bounds, data sparse, and data-rich conditions. So we're in review with that, so hoping to have something to share, in the next, say, five months or so, for that being a publicly available publication. If you are interested in any of those details, feel free to email me and I can share examples with you. But just to elaborate on those experiments, so we tested out-of-bounds prediction. So one of the challenges that you have with a data-driven approach, or one of the common critiques, is that if you train or build a model with colder climate, and then you attempt to predict warmer climate, it's probably not going to do a very great job, because the test data, the data that you're interested are out of bounds of it. So we evaluated that both based on training only with the colder years on the record, and then also only with training a model with springtime and fall temperatures, and then attempting to predict the warmer summer period. And in all of those situations, the model performance based on a root mean squared error of temperature was better for this process-guided deep learning versus a powerful but purely data-driven approach of a deep learning model that is time-aware, and also versus a calibrated process-based model. And those process-based models are the ones that I was focusing on for about the middle quarter of the talk or so. So I hope that answers the question. I know it's not satisfying that I don't have a paper link that I can send you to right now. The papers that we do have on this topic are, the main findings are that the modeling approach is more accurate in data rich and kind of data medium conditions, but those papers do not test the out of bounds predictions.
Thank you. So we got another question from Ryan. The methods seem fairly extensible to larger geographies. What are the limits to this approach, assuming there is enough data?
Great question. I would say the limits to this type of modeling approach is, and this is just a big issue for lake studies in general, is absence of information on lake depth. That is the hardest bit of information for us to dig up, and as I mentioned earlier, scanning or pulling data from PDFs from old bathymetric or maps from lakes, from the 60s or so, is one of the ways that we attempt to get all of that data together. So that's something that gets in the way of doing modeling like this at, say, the national scale, is you do need to make some assumptions about lake depth. And unfortunately, attempts to predict lake depth from other landscape characteristics aren't very accurate on a lake-specific basis. They can do a decent job at broad scales, but what we need to have is an accurate idea of how deep the lake is to do a good job with it.
Okay, we have a question from David. For those lakes where walleye are no longer projected to be supported, has there been explicit consideration of stocking those systems with a more thermal suitable species?
Yeah, so first I would say there are more thermally suitable species that probably don't need to be stocked in those lakes. So, for example, bass or bluegill, other warm water species are probably in most of those places there and doing just fine. No need for stocking. But of course, angler preferences play a role in what gets stocked. So there's some ongoing work that Ralph Tingley is doing with Craig Pockert at Missouri to extend this work in Wisconsin to look at, because we were just looking at walleye recruitment in this case, just saying, can the walleye naturally reproduce in this lake? Ralph is extending that work by also looking at adult life stages, which I think will be more relevant for stocking decisions. So we find that adult walleye have a different thermal response curve than walleye recruitment does. So we find a number of lakes where maybe they no longer are predicted to support recruitment, but adults would still do okay. And so those might be a good place to think about stocking versus places where recruitment is still going on, no need to stock there, or places where neither life stage is supported, and maybe it's time to start thinking about a more thermally suitable species and focusing management on that. Hopefully that answers the question.
Can you say more about the data sources for the lake temperature data?
Yes, so we have been working on different workflows to get together lots of different sources for lake temperature data, because the more we have, the better we can do at both assessing the quality of the models and also just building better models. So primarily the widest coverage and most diverse lakes for temperature measurements come from the Water Quality Portal, which is a joint project between the USGS and the EPA and combines both USGS NWIS discrete water temperature and all kinds of other water quality variables, and then all of the data in EPA STORAT. So that's, I think, 500 plus different contributors. And then lastly, there's one other federal partner in there, which is USDA. So that's our primary source of data. Additionally, we've gone after a couple data rescue efforts, and Gretchen in particular, with help from the Midwest Glacial Lakes Partnership for funding, worked with a student intern to digitize thousands and thousands of records that were in filing cabinets in Minnesota. And I don't know if you want to add anything to that, Gretchen, but those are primary places where we get data from. We're also interested in doing more with remote sensing data, but presently the accuracy of remotely sensed, at least from satellites, remotely sensed surface water temperature is just, it's not more accurate than we can model the temperature, with these new methods. So we're kind of exploring different ways to use it to improve our models versus use it as kind of a first-class water temperature observation.
How is surrounding land cover, such as local canopy cover and topography, quantified and utilized in the lake temperature model?
Good question, and I knew I had to skim over a bunch of these methods, which to me I think are fascinating because of my background in physical limnology. But I did skim over them because I thought they'd be a little in the weeds. So in order to take what information we can get for canopy and turn that into a lake-specific number that we can use in a model, what we do is we create a buffer around the lake. So it happens to be a 100-meter buffer, spatial buffer, and then we use that to mask out that, or to grab that portion of the national land cover data set to extract what the dominant land cover type is, and then we use a lookup table that gives us an estimated height for that. That's the way that we've been doing it for, I think, 3 years now. We did explore more complicated methods to get canopy heights using different remotely sensed methods, and we've got a paper on that I didn't show here, but we found the end result of that is that doesn't end up improving our models versus this simpler method of using the national land cover data set with a height-based lookup. And I think the details for that are covered in the Winslow et al. Paper, the 2017 data paper in Nature Scientific Data, that also includes a pointer to the first tri-state version of this data release.
Thank you very much.
Great, thanks all.